All right, team. So today we are taking a look at some unit conversions. Uh, this is going to be posted on our YouTube page. This also will be posted as a QR code kind of up in this area for later. So I'm also going to go ahead and apologize. I don't know what's going on with my camera. It's a little bit gritty. I'm sorry about that. For today, we are taking a look at the equation here. So we have P4 plus 5 moles of O2 creating this guy right here, this P2O5 situation. So we are looking specifically at the moles in grams and conversions here. So as a reminder, your conversion looks like this. You have 1 mole of any substance equals 6.022 times 10 to the 23rd particles, whether that's atoms, molecules, whatever. You also could have other units. You could get a mole of elephants is the example I feel like I've used a bunch this week. I don't know where you would get that many elephants. I guess they wouldn't be endangered anymore. That'd be good. But it doesn't really matter what your unit is. I use particles here because then I'm always right whether it's atoms, moles, particles is going to work. My amount in grams is going to come from the periodic table. We'll get a little bit of practice in with that today as well. So if I react 26.6 grams of O2 gas, how many moles did I react? So the first thing we have to do here is actually look at the formula that we're reacting. This is O2, not just O, so it's not going to be on the periodic table. We're going to actually have to solve for this formula mass. So looking at my periodic table here, I can find oxygen. Oxygen has 8 and 16 as the two numbers. This number on top is the atomic number. It tells me the number of protons. This number here, 16 is the molar mass. So in 1 mole of oxygen gas, I have 16 grams of mass. So I'm going to write that down. So for each of these moles, the reminder here is that O2 is an oxygen bonded to an oxygen. So that's what it would look like, right? Here's your oxygen bonded to an oxygen. That's the version of oxygen, folks, that we breathe. So to find the mass of O2 gas, I'm going to have 16 grams from the first mole and then 16 grams from the second mole of oxygen. Gives me 32 grams per mole of O2. I don't know why that almost was an exponent, but don't put it there. So now that I know I have 32 grams per mole, I'm able to set up my unit conversion. So in a unit conversion, the first thing we need to come up with is our conversion factor. So the conversion factor, especially if you are watching this and you are not a student, just to give you a quick reminder here, that is something like 12 items in a dozen, for example. So it is a set of values that hold the same amount of meaning, but with different units. So 12 inches in a foot, for example, would be a common one that we use. Another one might be 16 ounces in a pound. So when I write these, I'm going to write the thing that I'm looking for on the top of that and the thing that I know on the bottom. So I know that I'm looking for moles. So on the top, I'm going to write 1 mole. On the bottom, I'm going to include the molar mass. So one of the really common mistakes I see students make is that they'll put in 26.6 grams as their molar mass. That is not your molar mass. That is the number of grams that you have. Your molar mass here for this is in fact going to be that 32 grams that we just solved. So take a second and fill that in with me here. So what this fraction is essentially telling us is that 1 mole of oxygen has a mass of 32 grams, and that if you have 32 grams of oxygen, you have 1 mole of oxygen. From here, I'm going to multiply this by the amount of stuff whose unit I need to change. So I know the unit 26.6 grams. I need to change that unit from grams into moles. So in this instance, I'm going to multiply here the 26.6, sorry, all of a sudden reading numbers got hard, grams of O2. There you go. Put O2 everywhere. I know sometimes in class I would do it, sometimes in class I wouldn't do it. I'm not picky enough to need you to do it for when we're doing unit conversions. What I do need you to do is make sure that you're showing me all of your work. So in this instance, when I write it out, you can see where my grams of O2 and my grams of O2 cancel out, because this number gets multiplied by 1 for your numerator. So if you are putting this in a calculator, I'm going to use an iPhone calculator just because I'm assuming that most of us are probably using a phone calculator. I could type in 1 times 26.6. You wouldn't really have to do this step, right, because we're multiplying by 1 here, but, you know, it's good practice. Then I'm going to divide by 32 grams per mole, which again is that value that we solved earlier as the formula mass. So it gives me 0.83125, or not grams. It gives me 0.83125 moles of oxygen gas. I am going to round this, to be honest with you here. In class, for about 90% of what we've been doing, we've been rounding it to the hundredths place. Pretty much the only time we haven't been doing that is with the Avogadro's number, which is that 6.022 times 10 to the 23rd situation. I'm not picky. If you want to go all 5 decimal places, more power to you. I'm going to pretty much keep this sheet to 2 decimal places just to keep it a little easier for us as we work through these problems together. So I get 0.83, and I cannot leave that number blank, so that is in moles. And that is specifically moles of O2. All right, so then it says if we react blank moles of O2, how many particles did we react? The reason that's blank is I don't want to tell you the answer to question A in the actual answer, or the actual question for B. So for B, I'm going to just carry that number down. If we react 0.83 moles of O2 gas, how many particles did we react? So looking at our lineup here, we need to figure out what the relationship that we're going to look at is. So I know from reading in this sentence that I am looking specifically for the relationship here between moles and particles. And I just realized my highlighter, to me, it's like a super pretty mint green, and to you, it doesn't show up at all. So let me try that again. We are looking at the relationship between moles and particles. There we go. So I know that for every 1 mole, I have 6.022 times 10 to the 23rd particles. So now what we have to decide is which one is going to go on the top of that fraction. They give us the number in moles already. So we're going to put moles on the bottom of the fraction so that we can cancel moles out and convert over to particles. So that means particles has to go on the top. So I have 6.022 times 10 to the 23rd power par. Particles we're all going to just agree to know means par because I don't really want to have to write out particles 8,000 times on this sheet. I also will say that is the abbreviation, again, if you are not in class, that I use in class. So your student is probably used to seeing this written out this way. Underneath here, I'm going to put 1 mole. Sometimes students think they need to put this number, 0.83, or whatever we solved. That's not going to be the case either. We're trying to solve for the number of particles in that many moles. The only one we know for sure is that this is the number of particles in 1 mole. So to figure out how many are in 0.83 moles, I'm going to multiply here by 0.83 moles. I'm going to tell you a trick now. Sometimes I don't always share my little teacher tricks in class. I try to, but sometimes I forget. I don't know if I've said this in every class. Here's my trick for these. For these, I'm not going to ever do any division because I have 1 mole in the bottom. Dividing by 1 is going to give me the same number. So what I'm going to do instead here, 6.022, that gives me this guy taken care of. I'm going to skip the times 10 to the 23rd, and then I'm going to multiply just by the 0.83. The reason that I can do this is because that 10 to the 23rd power is not going away here. It's because I'm going to be operating in scientific notation, and I'm pretty comfortable with that. If you are someone who is still picking up some of the basics of scientific notation, or you're not super comfortable, it's okay to type in that times 10 to the 23. So I get 4.998. Again, I'm going to round that to 5. So I get 5.0 times 10 to the 23rd power, and that is in particles. So that 10 to the 23rd comes back into play because this number still fits into the scientific notation to keep that 10 to the 23rd. I basically just didn't put it in the calculator because I knew it was going to be there. It just saves students a lot of struggle with the math to just move that 10 to the 23rd over. Okay? So if that's one of the things that's really been frustrating for you, I'm not trying to tell you scientific notation is not important. If it wasn't important, I wouldn't spend time teaching it. What I am telling you is, if that's the tricky part, you probably have a good handle on this. Let's see how good of a handle you have on the next one. So if we are able to produce, sorry, I have a little sticky note that wouldn't let me move. If we're able to produce 47.12 grams of P2O5, how many moles did we produce? So in the last version of finding formula mass, I showed you how I like to add my stuff up. Just make a little list, do a little addition, easy breezy, beautiful, call it good. There's also a way you can do this where you do a little multiplication, and I'm cool with that too. So I know that I have 2 phosphorus atoms, that's P. So I'm going to look at my periodic table. Phosphorus has a molar mass, that you can't see, of 30.97. I'm going to call that 31 grams. You are totally close enough there. For a number like chlorine, where you're nice and in the middle, keep on those decimals. But like for carbon, nitrogen, phosphorus, where you only have to round a little bit to get to the whole number, selenium's another good one. Go ahead and round. Okay. So I'm going to have 2 times 31 grams. And then I'm going to do the same thing for oxygen. So I have 5 oxygens. Oxygen, remember, is 16 grams per mole. So 5 times 16 grams. Now I got to do a little math. So 2 times 31 is going to give me 62. 5 times 16 gives me 80. A little addition in there probably won't hurt us. And we get 142 grams per mole as our molar mass of this chemical. So from here, we're going to set this up again. So we know, let me get my handy dandy blue pen that has run away. There it is. We know our number of grams. We're looking for our number of moles. So here is my challenge for you. If you think you know how to set this up, pause the video here and do it yourself. All right. I am welcoming you back, my folks who have paused. If you didn't pause, no big deal. We're going to walk through it together right now. For this one, because grams is the unit that I know, I'm going to put it on the bottom. As a reminder, it's not this amount of grams. That's not the amount of grams in 1 mole. This is. So I have 142 grams here. We know, because we just did all the math to prove it, that this is 1 mole. From here, I'm going to multiply this by the amount of grams that I have, 47.12. Okay. So, bring my little calculator back over. 1 times 47.12 is going to give me 47.12. From there, I am going to divide this by my molar mass of 142. And it gives me, I'm going to call that 0.33. Okay, so I have 0.33. Okay. What is my unit on this ending number? Is it grams? Is it moles? Is it particles? What are we going to do here? This unit is going to be in moles. It definitely can't be particles. Particles doesn't ever show up in the math for this question, so that one is automatically kind of ruled out. From there, my grams on the bottom, boop, cancel with my grams on the top. I get left with just 1 mole. So this is 0.33 moles. I didn't give us enough space here really to do a ton of math. I'll fix that before I print these out for you guys. But in this one, 0.33 moles of P2O5. How many particles did we produce? So for this one, you are going to have to be patient with me for just a second. I'm going to throw a sheet of paper that I have over. That is a hall pass for those of you who can see that Trojan head through there. So to solve this out, we're looking for the relationship between moles and particles. So I know my number of moles. I'm going to put that on the bottom. 1 mole. The number of particles in 1 mole never ever changes. Always that 6.022 times 10 to the 23rd power. And remember, I'm just calling that PAR. I'm going to multiply this by the number of moles I actually produced, which is about 1/3 of a mole. And that's going to give me a number in particles. So go ahead, throw that one in your calculator for me. While you do that, I'm going to throw it in mine. Admittedly, we may get slightly different numbers if you rounded better than I did, because I just hit times on my calculator. If you actually wrote in 0.33 into yours, your number might be a little different than mine, and that's okay. We talked about this in class, but your periodic table might vary slightly from table to table. Typically, you're going to be within a couple of decimal places, but sometimes the rounding is different. When it comes to things like 1/100th of a gram, I am not worried. Okay? I know we talked about this in class as well, but I am a big believer in the ballpark method. I don't need you to hit a home run. I just need you to hit it in the ballpark. Right? You don't have to have the exact same number I have. You just need to be in the right ballpark. So, I'm going to multiply that by my 6.022. And I get 1.998. Again, I am not interested in all of those decimals. I'm going to call that 2. Okay, so I have 2.0 times 10 to the 23rd power, and that is in particles. All right, how are we feeling? We're halfway through our examples here. I'm feeling great. Love getting to do a little math on a Thursday. If you also love getting to do a little math on a Thursday and you don't feel like you need me, you are always welcome to pause the video, do a little work, come back to check in with us. If you are feeling like you are barely tolerating a little math on the Thursday and you'd kind of like to hang out with me more, I get it. I'm fun to do math with. What I'd like you to do for this next one is just take a second, set this bad boy up. There's always going to be the same set of steps that we follow. Okay? We're always going to start by figuring out, I'm going to move our captions over really quickly just so they're easier to see. we always are going to start by figuring out if we need to solve for a formula mass. So in this specific situation, we are looking at N2. Again, N2 is not going to show up on the periodic table. You're going to have to find that formula mass on your own. N2 is a chemical we've actually looked at before. This is nitrogen gas. We've looked at this in class a couple of times. Not, actual nitrogen gas. It's a gas, you can't see it. But we've looked at this chemical. In order for us to find the molar mass of N2, we need to take nitrogen's molar mass and double it, because you have 2 molecules of nitrogen here stuck together. So you can choose to add or you can choose to multiply. Because for this one, all I'm doing is doubling the mass, I'm just going to multiply. But first, I've got to find that molar mass. So if you don't have a periodic table, feel free to stick around and use mine. On this one, I can see that it gives me nitrogen's molar mass as 14.01 grams. If you want to keep that 0.01 around, again, more power to you, but we know Francis is going to round that down to 14. So parents, tutors, siblings, friends, what have you, whoever else might be watching this video, random YouTube people, my rule in my classroom is that if it ends in a 0.1 or blah, blah, blah. If it ends in a 1 or a 9, they can round it up to the next point, because with some of these you get weird numbers like 12.01. Sometimes we see oxygen expressed as 15.99. It just keeps those numbers a little bit cleaner for us, especially at the level that we're working at, right? This is kind of an intro chem course. So for my physical science students, you guys know that my job is to make this easy to understand in the best way that I can, right? It's not easy content, but if I can make it easier for you, let's do that. So I'm going to call this number 14 grams. So 14 grams per mole times 2 is 28 grams per mole. Some of these calculations, y'all, that I'm just throwing on the page are calculations that, for me, because I've done them so many times, I don't think about doing them anymore. If you need to plug them in a calculator, go ahead and do it, right? I have pretty solid faith that we can throw things like addition, multiplication into a calculator without me showing you how to do it. If you need me to show you how to do it, you know where to find me. I'm happy to help you. So I know now a relationship between grams and moles, which is probably good because I'm looking at a relationship here between grams and moles. So if we react 36.4 grams, how many moles do we react? Because we're looking for moles has got to go on the top of the conversion fraction here. So I have 1 mole of N2. In 1 mole of N2, we know there are 28 grams of N2. Okay. In the problem that we're looking at here, we have more than 28 grams. So in the last 2 examples we did, we ended up with moles that were only like fractions of moles. In this instance, you're probably going to get a number of moles greater than 1, because this number in the question is greater than the molar mass. It seems like kind of a silly thing to check. Overall, students tend to be pretty confident when it comes to this kind of number sense. But if that's something that you're struggling with, just predicting should it be greater than or less than 1, that's something we can talk about. So in this instance, because it's 28 grams in a mole, and I have more than 28 grams, I'm expecting to get a number greater than 1 as my answer. So I'm going to multiply this by my 36.4 grams of N2. I'll have you throw that in your calculator. Again, you get to skip that little multiplication step if you want to, because you're multiplying a number by 1. I got to clear my calculator out so we can use it. So I'm going to get 36.4 divided by that molar mass, which again is 28 grams. And it gives me a really pretty clean number, which is honestly refreshing. So I'm going to get 1.3 moles of N2. So go ahead, plug that into, not 4, Plug that into your next sentence here. We react 1.3 moles of N2. How many particles do we react? This is where kids sometimes ask the question, hey, Francis, it's N2. Wouldn't I have to double it? Keep in mind, this is not asking about atoms. This is asking about particles. Atoms are particles, so are molecules. So for this one, you would not have to double it. All right, we've already actually done the doubling of the nitrogen up here. If you double it again, you're going to quadruple your nitrogen. That's too much nitrogen. Leave it at 1.3. We also know in this question that we are looking at moles and the way that they interact with particles. So there has to be some sort of a relationship between moles and particles that we're able to fall back on. And we know that that relationship is 1 mole being equivalent to 6.022 times 10 to the 23rd particles. So that is going to be my conversion factor here. I'm going to have you take a second to set that up without me. I've told you the numbers. You just have to put them in the right order. We've talked before, too. I had a college professor that used to say the thing that you were looking for always had to go on the top so you could see it better. I don't think that for me that really helps to think about it like a little lookout, but if it helps you, do that. We're looking for particles here. So I would put that on the top like a little lookout. That many particles is not 1.3 moles. Don't put 1.3 on the bottom. That's 1 mole. Remember that the abbreviation MOL can stand for moles with the S on the end or mole singular. It's still MOL, which again is the most useless abbreviation in chemistry. You can add the E if you want. No one will judge you. From here, you're going to multiply. There will be some slight judging if you don't multiply by 1.3, but that's just because 1.3 is the only other number in the problem. So you're going to multiply by 1.3 moles. Just because, again, that's the only other number in the problem here, so you have to use that one. Your moles cancel out, and we get left with 6.022 times 10 to the 23rd times 1.3. There's my calculator. And again, I forget I have to put the calculator on the camera so we can see things. This is why I could never be an influencer. It's definitely not that I'm cringy and can't dance. So 1.3 times 6.02 gives me 7.83 when I round here. So 7.83 times 10 to the 23rd power. Again, I'm not multiplying in that times 10 to the 23rd because it's just easier to write it than to have to plug it into the calculator to just get the calculator to spit it back out at me. If it makes you happy, you should do it, right? We always talk in here about how if that's how your brain learns, if that's how your brain makes the connection, then do it. That's the joy about it. It's your brain. You get to teach it how you want. I'm going to scroll this up really quickly because what I don't want is for that to just be like hanging off in limbo land. All right. It is our last question together, which is kind of a bummer, but you know what? We're going to learn about ammonia, which is so fun. For this one, if we produce 44.2 grams of NH3, again, this is ammonia, how many moles did we produce? That is a great question to ask, but it's only helpful if we know how many grams are in a mole of ammonia. So what I would like you to do at this point is pause your video and solve out how many grams are in 1 mole of ammonia. All right, welcome back. So if you solved this out, awesome. If you were like just awkwardly waiting during that pause with me, thanks, I guess. Your molar mass of ammonia is going to require you to do a little bit of addition, but I think you'll be totally fine. We know NH3 has 1 N because there's no subscript and 3 H's because the subscript is a 3. So I'm actually going to list all these out. Again, you can do that multiplying method that we looked at above, but you don't have to. So nitrogen, we know, has a molar mass of 14 grams per mole. Hydrogen, we have not looked at yet, so let's take a look at that one. Hydrogen is one of the easiest elements to find because it's up here on its own. It has a molar mass of 1.01. Again, Francis is going to have you clean that number up just a little bit and call that 1 gram per mole. You're going to do a little addition here. When you do that little bit of addition, you should end up with 17 grams in 1 mole of ammonia. So, knowing that 44 is bigger than 17, I am expecting to have a number that is larger than 1. 44 is also a lot larger than 17, so if I had a number that was a lot larger than 1, I wouldn't be shocked by that either. You just need to keep in mind a little bit of scaling with those numbers. For example, I would not feel comfortable having 100 moles as my answer here. But if I had, for example, 3 moles, 2 moles, somewhere in that range, that might sound a little more realistic to me, okay? So go ahead, set up that conversion factor situation here. Remember, you are exchanging information between grams, oh, that was a horrible line, between grams and moles. Okay. So I gave you the framework. The next thing I'm going to do is actually take a second and just write in the unit. For some of you, I know that it's easier to just like fly through and plug these in the order we always go. What I'm trying to do right now is see, can you plug in the right numbers without me? So here's where I would put the units. All right. So for your conversion fraction here, you know that it's 1 mole. How many grams makes up a mole? Well, we just solved that right here. That's 17 grams per mole. That's how we read this. So G is grams, per is the slash, MOL we know is moles. From there, I'm going to multiply by the number of grams that I'm given in the question, which is this 44.2 number. 44.2 grams times 1 is going to be 44.2 divided by 17 gives me 2.6 moles here. All right, neat. If we produce 2.6 moles of ammonia, how many particles did we get? Go ahead and set up what is your conversion fraction going to look like to move from moles to particles? From moles to particles. You've got to ask yourself, do I know which 2 things I'm converting between? And the answer is always going to be the 2 things in the question. And do I know which order to put them in? So I'm looking for the number of particles. So I'm going to put 6.022 times 10 to the 23rd on the top. Get my unit on there, I almost forgot. And then 1 mole on the bottom. Multiplied by 2.6 moles here. When I do this without my 10 to the 23rd, my calculator gives me 15.6572, which is great. The issue is that I can't have 15.6 times 10 to the 23rd. It's improper scientific notation. So for this one, you have to do a little scientific notation conversion. So 15 point, let's call it 66 times 10 to the 23rd. I would probably give you at least half credit on. Because did you get the correct quantity? Yes. Did you get the correct scientific notation? Not so much. So in scientific notation, remember our rule is we only get one number before the decimal. So I need to move this decimal over there. So I'm going to have 1.566 times 10 to the what? Because you had to move your decimal to the left, you're going to add a number to your scientific notation. Remember, this number, 23, tells me the number of jumps between this decimal and where it really would land. So if I have to move to the left, I'm going to have to add another jump to the right to make this number have the right number of zeros. So for example, up here, 7.83 times 10 to the 23rd. I would have to move this decimal 23 little jumps to get to the real number, and I would have a ton of zeros here. So when I make this move, all I'm doing is just changing the exponent to reflect the right number of jumps. Okay, that's times 10 to the 24th. Thank you guys so much for doing a little extra practice with me. I know that on a beautiful May Thursday that there were probably other things on your mind, but I really appreciate your dedication to your learning and your science. I hope you have a great rest of your evening, and I'll see you in class. Bye-bye.